introduction. My name is Yangwook Kang from Samsung Electronics. Today I'm going to talk about the challenges in leveraging high-performance PCI-based SSDs in Keyvalue storage systems, and then our solution that uses offloaded Keyvalue store. We have observed that increasing I/O bandwidths of PCI-based SSDs are requiring more and more host system resources. So when you look at this figure, it shows the number of CPU cores used to saturate one NVMe SSD in various applications. When we use this benchmark FIO, at least one dedicated I/O core is needed to saturate one device when there is no other interference. But when you run a storage system on top of it, then it requires at least 4 CPU cores, and then their performance does not scale well with the number of devices. This is because there are already many compute and I/O intensive tasks in enterprise storage systems, such as journaling, indexing, and deduplications, and so on. And then these fast PCI SSDs are making the situation much worse. Because the CPU and memory are limited resources, this increased per device resource demands can limit the scalability or the performance of the system, because only a small number of devices in a node can be supported at their full performance. So the common technique people use is to install just 1 or 2 NVMe SSD in a system and then fill the rest of the slot with the slower SSDs or a hard drive. Another way to solve this problem is have a remote storage box that has a separate CPU for I/Os. Then the compute node and then the storage node can communicate via NVMe over Fabric or NVMe over TCP. But the problem with this approach is when we run a storage server on a compute node, there will be a lot of data transfer between storage node and compute node, increasing the network congestion. So we thought instead of using these extra resources, if you can offload a resource-intensive task to local compute-enabled devices such as GPU, SmartNIC, or even storage devices, then we can process data locally, and then local data transfer is much more efficient than sending it over the network. So our next question was, what can be offloaded from host CPU to provide both scalability and performance? There are many target tasks in the storage systems, but in this work, we focus on the Keyvalue store layer because it's widely used as internal data store in scale-out storage systems. And then it has a complex storage stack that includes indexing, logging, and then data reorganizations, and requiring lots of host system resources. So we thought if we can improve its efficiency and data utilization, then we can benefit the system running on top of it. Then we have to look at the existing Keyvalue store designed for SSDs. They already have mechanisms to utilize high bandwidth of SSDs. One of the common techniques is to use offloaded tasks to the background processes, so that the foreground processes can keep writing the requests at the speed of the devices with the minimal data processing, and then the background processes will reorganize the written data later. Another technique used in this Keyvalue store was to bypass kernel layers. So, for example, Aerospike uses a raw block devices using direct I/O and a user-level file system, and then RocksDB SPDK is a variation of RocksDB that uses a user space library and drivers to further improve their I/O efficiency. So to understand their impact, so we first measure the overhead of the I/O stacks. Between RocksDB and Aerospike, the RocksDB uses a kernel I/O stack, and then Aerospike uses a user-level stack with direct I/O. We didn't find much difference in performance because we think that's because direct I/O's goal is to bypass page cache and kernel file system, but the Aerospike has to have another user-level page cache and then user-level file system. So we didn't see much difference in between these two. But the RocksDB SPDK was quite interesting because it provided 2 times better performance and resource utilization than RocksDB. So after analyzing the source code and then their design, we found that in this RocksDB SPDK, the write-ahead log was disabled by default, while the RocksDB has used raw by default. So without raw, RocksDB's performance can be improved from here to there, around 30%. Then compared to RocksDB no wall and then RocksDB SPDK, the gap becomes 20%. That comes from the use of asynchronous I/O, huge pages, and large block sizes. And then we found that this 20% improvement on I/O efficiency was not enough to solve the problem with the scalability and performance trade-off, because there are other overheads from foreground and background processes. So when we measure the overhead of the foreground processes by sending the sequential workload to the system, then we found that RocksDB requires 8 flush thread to saturate 1 NVMe SSD, because RocksDB internally uses buffer synchronous I/O, and then has to write ahead log and then use AppSync to flush the data before writing actual key-value pairs. In the Aerospy case, they use a pool of synchronous I/O thread internally, and it doesn't allow one client to use all these I/O threads. So we have to have multiple clients to use all the synchronous I/O thread there. So they both requires a flush thread. That means when we configure the system to use 1 flush thread per instance, then it will require 8 instances. And the RocksDB SPDK saturate the device with 2 flush threads by disabling wall and utilizing asynchronous I/O. And then we also measure the overhead of the background processes, which we'll discuss later in detail. But the overall, we found that the amount of overheads depends on several factors, such as number of key-value pairs, size of the value, and the type of the workload. And then if there are many overrides or random writes, then overhead increases. And then if the background process cannot catch up the speed of the foreground processes, then it can make the foreground processes to stall or slow down. So overall, we found that the performance degradation is around 20 to 80% compared to the sequential performance. So even though they have multiple optimizations in the system, we found that the resource contention problem still exists. So if we can offload foreground processes without, we can say 1 to 7 flush thread per devices, and then if we can offload background processes, we can save another 2 to 3 background threads per devices. And then we have to decide the target device to offload this task too. And then we chose to use SSD because SSD is a permanent data store, and so there will be no extra data transfer for key value processing. And then SSD is already capable of supporting fixed length key and variable length values, so we can utilize some of these hardware components there. And then if we can avoid key value indexing in the host system, we can avoid metadata update overheads. So we try to find a right boundary between key value store and the host system for performance and scalability. In conventional key value stores has a multiple translation from file to key value pair to file to LBA, and LBA to page in the data paths, and then they do have index and journaling in each layer. Camel SSD was introduced in 2017 HPCA, but we found that supporting a fixed key of 8 bytes is not enough, because if the user key is greater than 8 bytes, we still need the index structure and journaling in a host system. So our goal was to eliminate the key value indexing in the host system, so there will be no dirty data in our system, so that then we can saturate the KV-SSD with the minimal CPU resources, that is 1 CPU per device. So in a KV-SSD stack, we have only the cache management inside, and then KV-SSD contains all this translation, key value pair to page, index management, iterate management, and coverage collection. So our Keyvalue SSD prototype is implemented as an SSD firmware that runs on the existing block SSD hardware. So that means block SSD hardware, block SSD can be switched to KV-SSD whenever it's needed. And then we built a whole firmware from scratch to support key value pairs. It has 4 main components: the key value request handler, hash-based FTL, iterators, and garbage collector. And then this API, we have like kernel-level device driver, and then user-level device driver. And then on top of it, there is a KV API, which is now part of the SNIA standard. So when we designed the internal data structure in KV-SSD, we have focused on these 2 features, variable length key support and key group support. So for the variable length keys, we cannot use a traditional index structure like trees and try, because device doesn't have enough memory to hold all these keys in their internal DRAM. So we use the hash-based data structure to limit the number of bytes per key value pair in SSD. And then when a request comes in, one of the index manager takes the request, and then using the first 4 bytes of the key, it groups it uses a group ID and then put it into the iterator bucket, and then hash the entire key and then put it to the local hash table, and then later merge it to the global hash table. And then garbage collector can look at this table and iterator buckets to delete the deleted key value pairs in the buckets and the table. So the reason we use the local and global hash table was to reduce lock contention between index managers. But more importantly, we are currently building the transaction feature. So we wanted to have a local hash table to hold the temporary data until it's being committed. And then when the user commits the changes, then we push it to the global hash table. And then there are key groups, which is indexed by the first 4 bytes of the key. And these are first written to the write buffer, and then later flushed to a iterator bucket that is identified the prefix. So then we try to compare the performance and resource utilization of Keyvalue SSD against the 3 state-of-the-art Keyvalue stores using 18 NVMe devices. Because Keyvalue stores cannot be saturated with, one Keyvalue store cannot saturate the devices, one device. So we assigned multiple instances of Keyvalue store per device to saturate their bandwidth. And then to do that, we have to make our benchmark program KV-SSD, because the existing Keyvalue benchmark YCSB doesn't support multiple instances of Keyvalue store. So this KV-SSD can launch all instances of Keyvalue stores at once, and then whenever needed, it uses the NUMA-aware CPU and memory assignment, and supports sequential uniform CPU distributions and YCSB ABCD workloads. And the server system we use is called the Mission Peak, that is a custom designed storage server that can saturate 18 devices. 18 devices can be attached to one CPU. It has each CPU has 48 cores with hyper-threading, and then we use Samsung PM983 PCI SSD, and the same hardware is used for both host Keyvalue stores and KV-SSDs. So we first run the sequential workload that generates minimal background overheads. Now, as you can see here, the KV-SSD provides linear scalability, and while using 1 core per device, 1 CPU core per device, and then other host-side Keyvalue stores throughput of the other Keyvalue store does not increase after 6 devices due to the high CPU contention right here. That after the CPU is saturated with 12 devices, the performance is going down like this. That's even when there's no background overheads. So when we have background overheads, the number is getting lower overall, and then we don't see any performance improvement after 6 devices as well. while the KV-SSD still shows linear scalability and then linear CPU utilization. CPU utilization also increases linearly. The reason why it couldn't improve its performance while the CPU is not saturated yet was there are lots of read-write amplifications. So the background operation writes 5 times more data to the devices, and this write amplification will make the device busy, but the throughput will not increase. And then we run YCSB workload that contains both read and write. Similarly, KV-SSD shows a linear performance without using cache. The KV-SSD shows a comparable performance with other hooks like Keyvalue store that uses lots of memory here. So when we use the per device, when you add per device LLU cache, 10 gigabytes of LLU cache per device, we can provide 4 times better performance with a 50% lower memory throughput than other Keyvalue stores. And then one good thing about this is there is only one thread accessing the device, so there will be no lock contention on this cache. And then instead of using page numbers as a key, or we can use a user key as a key to the cache. So it contains it doesn't have an internal. So it doesn't have. We can cache the exact amount of data we need. So in this paper, we show that the resource demands of host Keyvalue store make it difficult to utilize fast SSDs, and then the performance of KV-SSD scales linearly while using significantly lower system resources and outperforming conventional Keyvalue stores. And then now the API becomes a part of the standard, and then device commands are submitted for a review to an NVMe standard committee. This KV API and drivers are currently available as an open source, and a commercial version of KV-SSD will become available soon with around a 30 to 40% performance improvement and new features like transactions. That's all. That's the end of my talk. I'll be happy to take
questions.
Yeah, I was curious about providing range query or scan capability with a standard device.
Yeah.
The compaction issues are known to be most severe with sorted data.
Yeah, that's a good question. And a range query was always in our top, always in our to-do list. But what we have found is device is not capable of sorting all user keys inside. So we are thinking of it as we think that we'll need additional help from the host system to sort the keys. So the new version we are preparing for has a support for sorting, but the sorting is done in the host system. And then we have another type of device that has FPGA on it. And then maybe we can offload that sorting task to the in-device FPGA. So currently, this version of KV-SSD doesn't support sorting.
Question?
So the value size has to be a multiple of each size, or block size.
So normally in the Keyvalue stores, large block size is preferred. They use the block size is greater than 32K. 1 megabyte is very common. But in this case, we use 4 kilobyte as a block size because maybe the reason people want to use Keyvalue store is to use to store small Keyvalue pairs efficiently. If there are only the large blocks, then we can saturate the device easily, saturate the block NVMe devices easily with fewer resources. So,
yeah, my question is the value can be of any size, like of any byte size.
So we support up to 2 megabyte values. That is limited by the NVMe command spec.
I mean, does it has to be a multiple of block size? The value size, I mean. Can I have like
Oh no, it's a by the line. Value size is by the line. Yes.
And is there like a fragmentation issue in the space?
Internally in the device, yes, there is a fragmentation issue. So if the value size is less than 1K, there will be a fragmentation.
No, I mean, even the value size could be just multiple of block size, and still you have like insert and delete, right? And something like that, since you are going to have in the file system, right? And then you get the space fragmented, and then you have to move things around to make sure that there is a space continuously large enough to accommodate a large key value. It is something like a file system. You need to.
Yeah, but the only difference is flash memory doesn't support overrides, right? So we always try to find a free empty space in the device, and then write the data in the logging fashion.
I see.
So we don't have to reclaim the whole within these 30 data blocks, but it will be reclaimed by the garbage collector layer.
Let's next speaker.
Thank you.